There will be 2 talks today. Our first speaker is Professor Mythili Vutukuru. She is a faculty in the Department of Computer Science at IIT Bombay. Her main research interest lies in the broad area of network systems. She will be talking today on speeding up computation via multi-threading. Let's welcome her for today's.
Thanks, everyone. Thanks for having me here. Can you all hear me fine at the back? Okay. So this topic, I don't know how it'll connect with you all because I'm as far away from pure math as can be in my area. So I'll try to connect it up to the things that you guys may know. But please feel free to interrupt if at any point of time this is going way over your head. Okay. So I've tried to make this a little bit interactive, thrown in a little bit of puzzles here and there that I'll want you to use pen and paper and follow along just so you all don't sleep through it. So I'll try to make it interesting, but if at any point you're lost, please feel free to raise your hand and I'll take questions. Okay, is that good? Okay. So I'm from computer science, and our main job as computer scientists is basically what we call computation, right? Programs. You've seen some R program that was doing something. So there is obviously math is not just pen and paper and equations. There's a lot of computation that needs to happen for various reasons. For example, if you have unproven conjectures, this is a popular reason why computation is used even in pure mathematics. If you have, say, something like the Goldbach's conjecture that has not been proven, but people want to empirically verify it for a large number of values in order to say that, okay, mostly it is correct, right? So what is the Goldbach conjecture? So this is like the empirical proof of it. What does it say? Do you all know? You all have heard of it? Anybody has heard of what is the Goldbach's conjecture? So it says that, okay, it says that every even number can be written as a sum of 2 prime numbers always. There always exist 2 prime numbers for every even number, 2 prime numbers which add up to that even number, right? So while the problem statement sounds very simple, proving it has been very, very difficult. So what people have done is they've done like an empirical evaluation of it. So on the x-axis is a value of n, and on the y-axis is the number of times, number of ways in which you can write it as a sum of 2 prime numbers. Okay, as n becomes larger and larger, of course, you have a large density of prime numbers, and combinatorially speaking, there's some probability that 2 of them will add up to some even number, right? So as you can see, for larger and larger values of n, so you also have these bands. Do you all know why? So some numbers which are, say, multiples of 3 are more likely to be sum of 2 prime numbers and so on. So there's some probabilistic arguments for this. But anyway, so unproven conjectures like this, people, write programs that run to millions of even numbers and check for every even number how to write it as a sum of prime numbers, right? So for all of these things, now these are computations that take long amount of time to run. And similarly, you also have, mathematical equations that don't have closed form solutions, like, say, weather models and so on, for which also the solutions have to be computed via numerical methods, right? So for all of these things, we need to write some programs that compute things, and these programs run on large amount of data, take a large amount of time. So the question is, how do you speed up such computations? Right, so taking a step back, what is a computation? Like, you've written some simple R code that ran in a second or two. But if you are writing something very big, it will take many days to run, right? So any such computation, if you look at it, what is it? There is your program, your R program, your Java program, Python program, whatever that is residing. So every computer, maybe you would have learned this in your high school, has a CPU and has a memory. In the memory is where your program, your code, your data, variables, everything are in memory. Then the CPU fetches your program data and code and executes. That is how your program runs. Okay, so if you want to make this go faster, what do? Modern computers today have multiple CPUs. These are called multi-core systems. So what you can do is you can run the same program in parallel, multiple versions of it, so that it goes faster, right? So this is common sense and it kind of makes sense. So how many cores do you think are there on your smartphones? Your laptops. Huh? Phones are usually 4 to 8, laptops 8 to 16. So if you get a server, 64, 128, but if you have, large supercomputers have thousands of cores, right? So you can run the same program in parallel. Each of these CPUs is now executing a program, so therefore it will go faster, right? In theory, that is the idea. So for example, I will once again go back to Goldbach's conjecture and try to walk you through how you might make this go faster. Okay, so how do I, if I have to, count the number of ways in which an even number can be written as a sum of two prime numbers. Okay, how do I do that? So here is the algorithm that is given. So what I'll do is I'll first create a list of all the prime numbers. So you all know how to calculate what are all the prime numbers, say less than 100. How do you do that? You've heard of sieve of Eratosthenes. You know what it is. So start with a prime number 2, cross off every multiple of 2. Then go to 3, cross off every multiple of 3. Similarly, look through the list. Any number that has not yet been crossed off, which is a prime, go cross off all its multiples, right? And in the end, whatever you're left with is your list of prime numbers. So you pick some large number, say 100 million or 1 billion or whatever, compute all the prime numbers. Okay, so I have an array, a list where something is 1 if it is prime, 0 it is not prime. I represent all the list of prime numbers somehow. And then what will I do for every even number, 2, 4, 6, 8, blah, blah, blah. In fact, Goldbach starts from, doesn't hold for 2 obviously, but so you start from here, you go through every even number. What will I do? I will look at all the prime numbers less than it. I will look at every, so these are the, first I'll try to maintain these data structures. I'll try to count. I have the list of prime numbers. I have an array like this where every element is 0 or 1 if that particular number is prime or not. Then I want to, for every even number, I want to come up with a number like this that says how many ways I can write it as sum of prime numbers. Okay. So the way I do it is, this is my algorithm. This is the program I will write. For every even number, what will I do? I will look at every prime number below it, every P1 that is less than an even number. Then I will see that number minus P1. Say if I pick 90 and I pick a prime number, say 11, then I will look at 90 minus 11. Is this a prime? Oh, cool. Then I have a pair that adds up to 90. Then I look at 13. Is 90 minus 13 also prime? Cool. Then I have another pair, another pair. In this way, I will keep on counting how many such pairs are there that add up to that prime number. This is just brute force search, right? So this program, I will write it. So I have my array of primes. This I already first pre-compute using, say, sieve of Eratosthenes or whatever. Then I go through this array. This term for this is number of Goldbach partitions, it is called. Like every number, how many ways you can partition it as two prime numbers, right? So for every number, what will I do? I will go through this entire list again, count how many times, again, next even number, next even number. And the way you verify Goldbach's conjecture is, at the end of all of this, if this guy doesn't have any zeros, every prime number I found some non-zero number of ways of writing it as sum of, every even number I found some non-zero ways of writing it as sum of prime numbers, I'll be happy. Okay, then I can say that Goldbach conjecture is mostly true up to some large value. That is how people do it today. Now this is a computation. So if I want to compute till, say, 1 million, up to 1 million even numbers, I want to compute all the number of ways in which every even number can be decomposed as two primes and therefore verify Goldbach conjecture. Roughly, if I write on, say, my laptop, how long do you think this program will run? Up to 1 million? Days, minutes, seconds? Minutes. Good. That's a good guess. It'll take order of a few minutes. And if I want to go to, as you can see, this is going through the same array multiple times, right? So the complexity, as they call it, is actually, it is, from 1 million takes, say, 10 minutes, 2 million won't take 2 minutes, 20 minutes. It'll take more than that, a lot more than that, because the computation is just, you have more and more combinations to check, right? It's kind of growing a lot. So therefore, if I want to check to like billion numbers or something, it'll take like few hours. So how do I speed this up? So one way to speed this up would be, I'll do this. I will basically, if I have multiple cores, what I'll do is, for these even numbers, the calculation I'll run on one core. These even numbers I'll run on another core. Some other set of, so I will partition. Okay, this work I will split. I will do it on one core. This work I will do it on another core, and so on and so on. Right? I can partition my work across multiple cores. So that is the basic idea. Basically, all of these data structures, whatever data I have in my program, I will share across all my cores. And the work that I have to do, I will split it across the core so that it goes faster. Is the basic idea clear? So this is what real world programs do when they have large number of computations. They parallelize it. Okay. So, but not all computations can be parallelized, right? It's easy to see that not all computations, the one that I showed you, if I have the list of all prime numbers, checking every even number, which two prime numbers add up to every even number, I can do it for one even number on one core, another even number on another core in parallel. There's no dependency between the computations. Okay, so there are some calculations that are what are called embarrassingly parallel because they're so obvious. For example, matrix multiplication. This is commonly used in all your AI, machine learning, all of these algorithms today. You have two large matrices. I can just multiply one row, one column on one core, another row, another column separately on another core, right? I can parallelize this a lot. Therefore, these things can go faster very easily. But not all computation, again, you'll have to realize that not all computation can be parallelized. For example, the Siva-Eratosthenes algorithm that I told you about. Every prime number, strike out all its multiples. Can I run this in parallel? If for some number, the calculation for the numbers before it has not yet finished, can I just start my Siva-Eratosthenes wherever I want and say this part you do there, this part you do here? Why not? What will be the problem? Suppose can I say Siva-Eratosthenes for 1 to 10 I'll do in one place, 11 to 20 I'll do in another place? Exactly. So it may not be incorrect, but it will at least be inefficient, right? Because when you're doing 11 to 20 in another core and 1 to 10 here, you only have to do for 11, 13 and so on. You don't have to cross out multiples of 12 because they would have anyway been crossed out when you did the pass for 2, right? So things like that, right? So not every calculation, you cannot take every program and easily split it into, 10 parts, run it in parallel. Okay, so there are a lot of challenges involved in how to even parallelize programs, right? So that was just one example, but in real life, there are many examples where it's not just easy. It's not like, oh, I will buy some 1000 core computer, everything will be 1000 times faster. No, it doesn't work like that. Yeah. So Siva-Eratosthenes is this method of calculating if I have numbers, say 1 to 100. If I want to calculate all the primes, what will I do? I will start with 2. I will cross out all multiples of 2. Then I'll go to the next prime number, next uncross number 3, strike out all multiples of 3. Then strike out all multiples of 5. So in this way, whatever is not stricken out is a prime number. Okay, is that clear? So this algorithm, I cannot do 1 to 10 in one place and 10 to 20 in the other place, right? Because until I know something is a prime or not, if by the previous numbers it has not been cut out, I cannot really decide. Should I cut out all multiples of 12? No, because they would have been anyway cut out if I had finished the first part. Is that clear? So you cannot easily just split it into multiple parts and speed it up. Okay, so given a program, if it takes t seconds to run on one CPU, how much time will it take to run on n CPUs in parallel? Ideally, we expect it to be t by n, right? If everything in a perfect world, if everything can be parallelized, it is t by n. Okay, so your simple problems. If it takes 10 days to paint this building by one painter, if there are 10 painters, it will take 1 day. Each of them will paint one room in parallel. We can parallelize it. But real life programs cannot always be parallelized. Okay, so usually there will be some part of the program that cannot be parallelized and only the remaining part can be For that part, no matter how many cores you have, you cannot make it go faster, right? Because everybody has to do it together. And then the remaining part, the fraction P, can be run in parallel. In such cases, the actual runtime will be for this 1 minus P part, that fraction of T will stay as it is. Suppose half your program can be parallelized. Okay, that half will be speeded up. If you have n cores, it will run in lesser time. But the remaining half that is not parallelized will go at the same speed. So you will not get, if you have 10 cores, you will not get a speed up of 10. It will not go 10 times faster. It might go 4 times, 5 times, whatever, 3 times faster, right? So in fact, computer scientists spend a lot of time looking at programs, deciding how should I structure my algorithms, my computation, my programs, such that things can go faster, such that I can say this part can run independently, this part can run independently, that part can run independently, and everything can actually go faster. So if you study computer science and algorithms, there's an entire area devoted to how do I make things go faster, and by running them in parallel, by making them more parallelizable. Okay, is that clear so far? You all are with me? Any questions, guys? Any questions so far? Okay, so this was one part of the question, right? Given a program, you have to decide what parts can be parallelized, design your, for example, the Siva Eratosthenes was not very parallelizable. The other part was parallelizable. Look at your program, see, okay, this part, I can actually run it in parallel, make it go faster. So people who write real programs make those decisions. Now the next question comes up, once I have decided, okay, this part of my program can run in parallel, right? You have some large R program, MATLAB, whatever, C++ program, you decide, okay, all my computation is such that it can proceed independently. Different parts of my program can run independently. Now, how do I make it run independently? How do I tell my computer do this in parallel? Okay. So for that, once again, there are many ways to do it. One way to do it would be I will simply run multiple copies of my program. Okay. If I have an 8-core machine, I will run 8 different copies of my program. Each program will run on one CPU and it will go faster. Right? But this may not always be the best way. Why? Because now, first of all, your program is there in main memory, it is consuming memory. You have this, large, say 1 billion list of first prime numbers up in the first 1 billion numbers. Now I have, this will be some large, it will consume some space in your computer. Then I say I have 8 copies of this large data structure saying, oh, this is for this CPU, that is for that CPU. Kind of doesn't make sense, right? It is very inefficient. So therefore, what modern systems once again do is, we have a concept of what is called a thread. You can think of a thread as sort of a lightweight program. Okay, if you have one program that is doing some computation in your memory, you can create multiple threads on it. Saying multiple threads are almost like programs, but they are lightweight. They all will run in parallel on your different CPUs, but they will use the same program code, the same data structure, same list of prime numbers, everything, right? It is as if you have a large program, you have all the things that you want to do, and somebody will be running here, somebody else will be running here, somebody else will be running here. So threads is simply a way in which when you write your program, you can tell the computer, hey, use the same program. I will not start 10 different programs. I will only run the program once, but internally, you please, make some lightweight copies of it and run them in parallel on the multiple CPUs. Okay, so programming languages today provide you with ways to do that. So again, I don't know how much familiarity with programming you all have here, but this is the only piece of code I will show you, which is if you have, this is a C program, a C++ program. When you have a program like this, what you can do in your program is you can say create a thread. And for every thread, you can give some function, some piece of code it has to run. So this is saying I'm creating one thread and I'm asking this guy, you do this job in the program. I'm creating another thread, I'm asking it to do this job in the program, right? So I can basically, there are ways. Don't worry if you don't follow the syntax here. Syntax is not important. But The point I'm trying to make is you can write programs. All modern programming languages let you write programs in a way where you can specify inside the program key, run these things in parallel. This part of the program can run separately, this part can run separately, that part can run in parallel on another CPU. You can specify that to your computer when you write your program. And by doing that, you are able to realize this parallelism in your code and make your computation go faster. Okay, is this clear? Any questions so far? Yes? No, this is not recursively. This is basically this thread will only execute this function. That's all. This thread will only execute this function. And after this function, it will end. Okay, so. Okay, so now, okay, that was easy, right? So what is the big deal? What will I do for the next half an hour? It turns out that this is not easy, right? Saying multiple people, kind of, multiple entities execute on the same data structures on the same program. As a concept, it is all nice. But when I try to realize it in practice, a lot of things can go wrong, right? So as any of you, if you worked in a team project, you know how frustrating it is, right? It is not always easy to three of you to read from the same book or, share the same computer. There are always issues sharing things, accessing the same shared data. So it turns out threads are also like us. They don't really work very well together when everybody has to work with the same program. A lot of things can go wrong. Okay, so I'll try to give you an example of things that can go wrong and then try to tell you how we solve it today. Okay, so for example, this is a very simple problem, right? So I have two threads in my program and I have a counter. I have some variable counter whose value is 0. And both these two threads, what they do is they increment. Both of them are sharing the same program. And in the program, I have written code to increment this counter by 1. And I have created two threads and I have asked both of them to run this piece of code, right? I said, okay, both of them, instead of one program incrementing the counter 2 times, I have asked two threads in parallel, you please increment the counter once each. What do you expect the value of the counter to be at the end of it? I start at 0, I increment it twice by 1. We expect it to be 2, right? This is 1 plus 1 is 2. Okay, but in practice, when you run it, it may not always be 2. Sometimes it will just be 1. Right? You can actually verify it in computer. So what is happening? I mean, after all of this computer science, have computers forgotten how to add numbers? No. So what is happening is when threads share data and execute in parallel, a lot of bad things can happen for the following reasons. So this is what is happening. So you have this counter which has a value of 0 initially. This is there in your memory. And then this counter, when it has to be incremented, when you have to add 1 to the counter, the way it happens, the way modern CPUs do it is that counter will be stored locally somewhere in the CPU in what is called a register. A register is nothing but sort of temporary storage. Now yours, yes? Counter is any integer, any number, right? It's something that keeps a count. Okay, I have a variable in a program, or you can think of it as there's a number whose value is 0. Okay, and I have asked two threads in my program to increase this by 1 each. Okay, this thread is supposed to increase it by 1, that thread is supposed to increase it by 1. So from 0, it should go to 1, then 2. Right, that is what I want to do. Now this counter is there in my main memory, a value of 0 is stored in it initially. Now what will happen? This one thread is running on this CPU, another thread is running on this CPU. So what will, the way any computation happens in your computer is you get things from memory, then the CPU works on it and puts it back into memory, right? Every laptop you look, there is some memory inside it and there is a CPU inside it. If you open the lid of any computer, you will see a CPU that is made by people like Intel. There'll be a chip, a CPU chip inside, there'll be a memory chip inside. Okay, memory is the storage, CPU is the one that does the calculations. Now the way the CPU, has to add anything to a number is it will bring that number from memory to its internal storage. increment it and put it back. Right? Is that clear? So that is what I'm saying. This, if I do counter, is counter plus 1. This is how you write it programmatically. This is the syntax in any programming language. This basically becomes, you will load the counter into a register. What is a register? It is just some special storage inside the CPU. So I will get the counter value of 0 here. I will increment it to 1 and I will take it back into memory. So then this value becomes 1. Then the next thread will run. It will get this value 1 into its register, increment it to 2 and put the value back here. So this value becomes 2. Right? So that is how it happens. All your computers, any computation that has to happen, you will first take it from memory. You will do something in your CPU with it, put it back into memory. Right? Everybody with me so far? This is how it is supposed to happen. And this is how all modern computers work. They will take something from memory, do some calculation, put it back into memory. Now, yes? So normally it is stored in your memory. Your computer has a memory that is distinct from your CPU. Right? If you remember in high school, I don't know if you guys did, there is CPU, there is your keyboard, mouse, and there is your DRAM. RAM it is called, right? Random access memory. There is some RAM in your computer, in which all your program data in your R program that you guys were writing some time back, there was X1, X2, blah, 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 all of these. Where are all, they are all stored in your memory. Okay. And then you take it from memory, do some calculation on it, put it back into memory. Okay. Is that clear? Everybody is with me so far on the story? Now what can go wrong here? There is something that is 0 in memory. I take it into one CPU, add 1 to it, put it back. I take it into another CPU, add 1 to it, put it back. It should be incremented by 1 and 1, therefore by 2. What can go wrong? Exactly. So what can happen is as follows here. So suppose there are two threads, T1 and T2. The first guy took this counter value, from memory, which is like a chip on your computer. Now, all of these guys are separated, right? There is a memory chip somewhere on your motherboard. There is your CPU chip. There is some non-trivial delay in getting things from here. It typically takes a few nanoseconds. So the first CPU went to memory, got this counter back, and it is working on it. Meanwhile, the other thread came. It also read the counter from memory. Before this guy could put this value of 1 back, before this guy could increment and put it back, the second guy again took the old value of 0. This guy also said, oh, it is 0, I'll make it 1. And then what? Both of them have a value of 1, then both of them will put back 1. Right? This guy will also update this to 1. This guy will also update this to 1. So this is in parallel, right? Sometimes when you don't coordinate with your friend, two people will bring birthday cakes at the same time for a party because they couldn't coordinate with each other, right? So it's nothing different from that. These two guys didn't really coordinate with each other. Both of them thought they were incrementing a value. So both of them read the value from memory. Both of them did their CPU operations. Both of them put it back. And at the end, they realize, oh, you also incremented, I also incremented. But what is the result? It has only been, the final value has only turned out to be 1. Can you all see? Because both took the value of 0, both incremented, and both wrote back 1. They didn't do it one after the other. They did it in parallel. Is this clear? What's happening? The problem is clear. So this is in fact what is called a race condition, or this is a frequent problem that happens when people write multi-threaded programs. Of course, there are ways to prevent this. In all modern programming languages, there are ways to prevent this. But if you don't do it correctly, people still make mistakes. And these kind of error conditions that happen due to, and again, this won't always happen, right? Sometimes it might all go one after the other, sometimes. So this is like sometimes a bug happens, sometimes it doesn't happen. So these kind of errors with multi-threaded parallel computation are very, very frustrating to debug and very difficult to find as well. Okay, so it is not easy to say, oh, I have written some program, go parallelize it, run it in parallel. There are all of these issues that happen. Okay, so what should we do? So in general, any programming language that lets you create threads also provides you with mechanisms to coordinate between the threads. It is not enough to simply just create threads and say, oh, all of you guys run in parallel on all the CPUs, life will be good. No. So all of these threads have to somehow coordinate. They have to say, oh, if this thread is updating some shared variable, some shared data, the other thread has to wait for it. We have to do something what is called mutual exclusion. That is, only one thread at a time can read this counter and update and put it back. If you are not accessing common data, you can run in parallel, right? If you are counting, if one guy is counting number of prime pairs for one even number, another guy is doing it for another even number, you are all doing disjoint things, separate things, you do in parallel. But the minute both of you are touching the same memory location, the same variables, you have to coordinate. You have to do mutual exclusion, only one at a time. And there are various other things that threads might want to do. For example, one thread might say, oh, only after I do this calculation, you proceed to the next part of the program, right? So you might want to do some kind of signaling. In general, when threads in a program have to work together, there are many different needs for them to coordinate with each other. A thread has to say, oh, is any other thread touching that? I won't touch. Oh, did that thread finish it? Only then I can run, right? So we need this kind of control in our programs. When we write multi-threaded programs, we need control on how the threads run, in which order do they run, so that we can get some correct behavior. Otherwise, if you just leave them to do whatever they want, it will be all anarchy, right? All sorts of bad things will happen. So therefore, all programming languages provide different methods to do this. In this lecture, I will just discuss one of the methods. There are many, many ways to do this. I will just discuss one cute little idea called a semaphore, simply because I thought this is something that it has a little bit of a math flavor to it and will probably interest you guys. But note that this is not the only way. There are many other ways to coordinate between threads. I'll just describe one way to do it, which is using semaphores. So semaphore is nothing but it is like a, yes. Yeah, so that's a good question, right? So which is why threads should not be in this mutual exclusion state all the time. There should only be some small parts of the program which are shared that you do in mutually exclusive fashion, but people should write programs in such a way that most of the code, if you are updating different integers, different numbers, then this problem doesn't arise, right? This problem was arising only because both of them are updating the same counter, both are incrementing the same counter. So therefore, some parts of the program, it is inevitable that you have to share. For example, the total number of Goldbach pairs, if I want to count, I have to at some point look at everything that all threads have done. For such things, you need mutual exclusion. But for most of the times, you have to write your programs in a way that every thread has its own variables, has its own work to do without having to coordinate with the other threads. Right? But sometimes it is inevitable that all threads have to update the same variable, in which case we have to use mutual exclusion. But if your program is such that everything can only be done with one thread at a time, there's no point even using multiple threads. Okay? Any more questions? Okay, cool. So there is something called a semaphore. Okay, so this is a little bit tricky to get a hang of. So please bear with me. But once you get a hang of it, you'll see that it is actually pretty neat. Okay. So these libraries that provide you with threads also provide you with some special variables, some special objects called semaphores, which multiple threads can actually share these semaphores and use these semaphores to coordinate between them. Okay. So the semaphore is something like some middleman, somebody who is intermediating across all of these threads, helping them achieve some kind of a coordination. And whenever you write programs with threads, and if you have these needs that, oh, whenever I'm accessing this portion of my program, there should be mutual exclusion. If I have any such needs, then what I have to do, I have to use something like semaphore to do this coordination. Okay. So how do these semaphores work? These semaphores work as follows, right? So understand the logic and then we'll see why it is like this. So here is what it is. A semaphore, every semaphore has some counter inside it. It is basically something like a counter. There is, you all understand what is a counter? Some number, right? It is 0, 1, 2, whatever. It's some integer number that is there. And threads, multiple threads that are using the semaphore, say if you have threads T1, T2, all of these threads can either, increment the semaphore, do a up operation on it, or do a down operation on it. Okay, so these are the two operations that you can do on a semaphore. Just like on integers, you can add, multiply, whatever the set of operations you can do on integers. Similarly, on a semaphore, there are two operations you can do. It is not fully an integer. It is something like an integer, but it is a little bit more. You can do two operations on it. Okay, so what are these two operations? I can do a down on a semaphore and I can do a up on a semaphore. And when a thread in a program does a down on a semaphore, if that semaphore value is negative, then that thread, the semaphore will basically hold on to that thread, will not let that thread run anymore. Okay, that thread ends up sleeping, waiting. It cannot execute anymore if it does a down and the value is negative. But if the value is positive, it can continue to run. And when you do an up operation on a semaphore, what happens is the thread that does an up operation increments that counter, and if any other thread is sleeping, it will wake it up. Okay, so this might all look a little bit complicated, but please bear with me. We'll run through an example. And, by using these operations on semaphores, threads can actually wait and coordinate and do all of these things with each other. I'll show you how, right? Hold on for a minute. I'll show you how. Okay. So here, so let us take a very simple example, right? I have two threads in my program and I want mutual exclusion. Okay. I have thread T1 and I have thread T2 and I want mutual exclusion. Whenever they're accessing any shared data, I don't want both threads to access the data at the same time. But how do I do that? When I'm writing a program, when you write a program, do you have any control when the program runs, on which CPU is it running? How much time is it running? Oh, is the other CPU accessing the... You have no control, right? You just have to write the code and, trust in God and hope that it all runs fine, right? But we as programmers have no control over the CPU. This is all managed by the operating system. We have no control. So what can we do to have some control? What we can do is every thread, before it accesses any kind of shared data, whether it's a counter or something, before accessing this data, in order not to, have this headache that some other thread may also be reading that data and doing all of those things, what it can do is it can call down on some semaphore before accessing the data, and after accessing the data, it can call up on the semaphore. If I do this, it is guaranteed that only one thread at a time will access the shared data. Why is that so? I'll show it to you now. Okay, so suppose, the semaphore value initially is 1. Okay, so this semaphore is initially, I have initialized it to 1. Now, when thread T1 does down on the semaphore, what happens? The semaphore value becomes 0. Yes, down decrements the value and the value is not negative. So therefore, thread T1 will not wait. It will just continue its execution. It will go on. It will access this shared data. Then it will increment the semaphore value back to 1. Now, while T1 is, accessing some shared data that it does not want T2 to look at, when it is accessing some data that requires mutual exclusion, at that point, if T2 also tries to access the data, what will T2 do? T2 will also do down of the semaphore. Why? Because that is how you write your program. You write your program with semaphores in such a way that anytime you want to access any shared data, first you will say down, you will call the down operation on the semaphore, then you'll access the data, then you'll call up operation on the semaphore. That is how your code is written. And when you write your code like that, what is happening? T1 access this data, the semaphore first, the counter, the semaphore's count, basically the semaphore's internal count that was there became 0. Then you access whatever mutual exclusion stuff that you want, you're doing it here. While you're doing it, if T2 starts, now the semaphore is 0, it became -1. Now what happens? T2 cannot proceed anymore. Okay, so your code halts over here. It is like that thread sleeps, that thread waits over there. So the operating system will not allow this program to continue further. That is the point of the semaphore. Okay, you decrement the value. The minute this counter, the semaphore's counter is negative, T2 will just wait. And therefore, it cannot access the shared data until T1 increments the semaphore. When you do an up operation on it, then any waiting thread will be unblocked. It will go access the shared data. Right? So in some sense, this is acting like a guard, a gate that is only allowing one thread at a time to go through. Is this point clear? By using semaphores, now it might look like such a convoluted way to do something simple, but I'll show you. There are many other interesting things that you can do using semaphores, not just this. Time permitting, we'll run through a few more interesting things. But is this idea clear? The semaphore basically has a counter, and in your programming language, every time you have anything that you don't want multiple threads to do in parallel, what you're going to do is you're going to call down on a semaphore and access whatever secret stuff you want to do alone, then call up on the semaphore. While you're doing this, if any other thread on any other CPU is running and it tries to do the same thing, it cannot proceed forward. At that line of code, it will be stopped. Okay, the operating system will ensure that it is stopped. Right, is this clear? Right, now what if they are not running together? They are running one after the other, then also this will work. This guy made the counter 0, increased it to 1, then the second guy runs afterwards, not in parallel. Then the counter once again from 1 goes to 0, doesn't have to wait. So if they are running one after the other, they are not made to wait. Only if they are running together while this guy is running, if the other guy comes in, the semaphore ensures, because the counter value captures it, it ensures that only one thread at a time runs this. Is this clear? So suppose I want to ensure only n threads at a time are accessing some shared data. Not one, not mutual exclusion, but I only want n threads at a time to be accessing some shared data. Then what can I do? Huh? So my semaphore counter will be initialized to n. Right? Can you all see that? If I use a semaphore, very good. If I use a semaphore initialized to n, then multiple threads, n threads can do down, enter, the shared region, keep accessing the shared data. They are all fine. But when the n plus 1th thread comes, right? If I want to allow 10 threads, the minute the 11th thread comes, then my counter has become negative. Then it will not be permitted anymore. Suppose I want only, in some server, I only want 10 people watching videos on some server on YouTube. The minute the 11th user comes, we'll put a semaphore like this with a count of 10. The 11th user will not be allowed to proceed until one of the guys leaves and does an up and wakes up the sleeping thread. Right? In this way, using semaphores, you can actually control how programs run, which part of the code your program is executing, how many threads. Even though you've created all of these threads in parallel, you can exercise some control on which threads are running in parallel and which threads are waiting and so on and so forth. Is that clear? Everybody is with me so far? Any questions? Okay. So now I have a different requirement. What I want to do is, I have 2 threads in my program and my goal is not mutual exclusion at this point, but these threads have kind of split up the work. Maybe one of the threads is running my Siva of Eratosthenes, preparing the list of primes, and then the other thread is computing the number of Goldbach partitions, right? So the second thread cannot actually run until the first thread has finished its job. There's no point starting without, this list being ready, right? So in such cases, how do I do? How do I coordinate? I've written my program. I have said one thread you do this, the other thread you do that, and they're both running. I have no control over my CPU which thread is running where, but it doesn't make sense for the second thread to run before the first thread has run. So how do I exercise this control in my program? Once again, I can use semaphores. I can use a semaphore. Now I will set the semaphore counter to 0. And what I will do is the first thread will do its work and call up on that semaphore. The second thread, before it starts its work, will call down on the semaphore. Okay, this is how I will write my code. Once again, this is a completely different scenario. This is not mutual exclusion. This is signaling. I want to enforce a certain order of execution of the threads. It is not only one thread at a time. I want it to be T1, then T2. The way I do it is, I give both of them the same semaphore to 0. So suppose T2 starts before T1. On some CPU, T2 starts to run before T1. This guy will do down on that semaphore. The value is negative. It will wait. Okay, which is what I want. I don't want this guy to run before T1. So this guy will wait. And after T1 finishes the semaphore counter, it is incremented and this thread is woken up, and then T2 will do it. After this guy finishes the sieve of Eratosthenes, then this guy is going to run the Goldbach partitions. On the other hand, if T1 has, you have no control over which program runs where on the CPU, right? Suppose by God's good grace, T1 ran first. It finished its job. Then the semaphore counter has become 1 now. So now if T2 runs next, the down operation, the counter is 0. It is not negative. It will not wait. Right? So somehow you have ensured that if T1 has already finished, T2 need not wait. It will run. But if T1 did not finish, then T2 can run. Then T2 has to wait. Right? If T1 did not finish, T2 has to wait. But if T1 has already finished, T2 does not have to wait. Right? So again, using semaphores, you have kind of ensured this kind of signaling between different parts of your program, even though you really have no control on the underlying CPU, what is happening. Yes, is this clear? We've again used semaphores and achieved a different kind of coordination. Any questions? Yes? Yeah. Yeah, so in Python, normally when things are running line by line, there's only single thread of execution, right? But if you create multiple threads, only then these problems come up, right? I'm only talking about when your program, now the R code you guys ran in the morning was just single threaded code. But if somehow you can create threads and make multiple things do at the same time, then this will come. Before I initialize my x1, x2 arrays, I don't want to plot, right? All of those things right now, we don't have you may not have written this kind of code to see this happening. Okay, does that answer your question? Okay, so now I have another puzzle for you. I have two threads, both have to run 2 steps, right? So I want T1 and T2 both to do something first, and then only after both of them have kind of, this is called a rendezvous situation. Once both of them have met, have finished some initial steps, only then they should go to their next step. Right? Both these threads have 2 parts of work. Both should finish their first part, only then they should wait for the other person. Just because T1 finished its first part, it shouldn't go to the second part. It should wait for T2 also to do something and then go to the second part. Okay, is that clear? So the way I do it is as follows, right? So I will use 2 semaphores. I will use a semaphore T1 done and T2 done. What I'll do is I will do up on the semaphore, down on the other semaphore, right? So with 2 semaphores, I'm achieving the signaling. Can you all see what is happening? This T1 finishes step 1, increases this semaphore to 1. And then suppose T2 is not yet done. T2 has not yet increased its semaphore to 1. Then T1 will wait here at this down operation, because this semaphore was initially 0. It became negative. Now it will wait. After T1 finishes its step and it does its up, then this guy can proceed. And after this guy does the up, this guy can proceed. Right? So we have used 2 semaphores somehow. We have ensured that only after both these threads have finished, maybe both threads are doing some initializations in the code, or, creating your x1, x2 arrays, all of that, only then they're going out to the plotting part, something, right? You are ensuring that the first parts are done, only then going to the second part. So again, these are all patterns that occur in real computer systems. When you have real life large systems running, which have multiple threads, this is all the stuff that computer scientists do to figure out these patterns. I want this to be done first and that to be done. Only after all of this is done can I go ahead and do it. Okay, can I go ahead to the next step of the threads? Is this clear? Is this going over your heads? Started to go over your heads or not yet? Is it okay? Okay. So it's just the previous solution, but I just flipped the up and down statements. Right? So it is the same question, but what happens here? So think about this. What I've done is I have said that 2 threads both have to do 1 step and then they have to do the next step. And to coordinate, we've given them 2 semaphores. We have said that you do up on your semaphore and then do down on the other guy's semaphore, wait for him. This guy also does up and down. Now what I've in my previous solution, I had it like this, up first and then down. Here I've just flipped these two lines of code. Is this correct? Will this work? Now these semaphores are both initialized to 0 and these threads are running. What will happen here? Exactly, very good. Can you all see what will happen? So T1 runs, does its step 1, the semaphore is 0, it does down on it, becomes negative, T1 waits here. It has not yet done its up operation, it just waits here. T2 also starts. It's like two people have gotten into a fight, they're both waiting for the other person to blink, right? So that is what this guy also says, he's waiting for that guy to increase his semaphore, this guy is waiting for this guy to increase his semaphore, and both of them have not yet come to the up. Will they ever come to the up? No. They both end up waiting for the other person, right? Again, the point I'm trying to make it, when you write code with semaphores, there are all of these. So this is what is called a deadlock. Okay, frequently it will happen that people are writing these large multi-threaded programs. They're trying to coordinate between these multiple threads. But what is happening? Somehow they just interchange. You know, some developer somewhere will just flip two lines of code in the middle of the night, and then your server is crashing. It is not doing any work at all. Your system is hung. Why? Because instead of incrementing something and then waiting, you started to wait first. That guy is also waiting, you're also waiting, both of you are just staring at each other, nothing is happening. Your system does not progress at all. Both these threads end up waiting unnecessarily. Such situations where your system does not make any progress is called a deadlock. Okay? So I'm almost out of time, so maybe this is, I will probably skip these things. There are a few other such examples that I have puzzles. Maybe I can share the slides with you all later. If you all want to work it out, you all can do it. But I just want to end this talk saying that this is just one, I've shown you just one snippet of semaphores and how they coordinate. But in fact, there are many, many such mechanisms available. And writing multi-threaded parallel programs is very tricky. You have this part about shared data getting updated inconsistently. The minute you use all of these semaphores and all to coordinate, you have a whole bunch of other issues. And it's not just semaphore, there are a bunch of other such mechanisms available. And parallel programming, again, with AI, ML, all of this coming up, parallel programming is the hot thing. You have CPUs, even GPUs that do a lot of parallelization, and there are many programming frameworks available to write parallel programs. And it takes a lot of effort to think through how you will write a parallel program, what parts can be parallelized, what parts can run in parallel safely, how do I synchronize, how do I avoid deadlocks, how do I get the desired results I want, right? So this part of computer science is usually taught in an operating systems course or any computer systems courses, because we frequently have to deal with multiple threads doing computations and so on. And there are a lot of challenges and a lot of interesting puzzles around this. So this on my webpage here, you have more of the, if you're interested in learning more. And the other thing I wanted to share with you is there's this book called Little Book of Semaphores by Alan B. Downey. This is freely available on the internet. So this book has several of these puzzles. You really don't have to know much of operating systems or computer science. These are just framed as, for example, this puzzle over here is, you have hydrogen and oxygen molecules, atoms coming in. How do you form water molecules? They're all framed as very simple toy puzzle problems, but using concepts from computer science, from semaphores and from threads and synchronization. You use these concepts in order to come up with interesting problems. And again, these are not toy problems, right? These are actually real world patterns that occur in real world systems. So you can get a fair bit of understanding of real world design patterns by looking at these toy problems and playing around with them. So if you guys are interested in these kind of things, you can look up this book. So there are still a few more problems that are probably slightly more complicated, but I didn't have the time, so I won't go into it, but you can look it up online to find more such examples. Okay, so I will stop here and I will probably take any questions, and I'm also available if you want to chat one-on-one after this talk and before the next talk starts. Okay, thank you all.
Thank you, ma'am, for the wonderful talk.
Thanks.
Are there any questions?
Yeah. So what I've told you so far is CPUs, right? On your computer, you have a central processing unit. You have a chip made by Intel that actually has multiple parts. It can run programs in parallel. So typically on your phone or your laptop, you have 8, 16 CPUs. But sometimes what you need to do is you need to run many things in parallel. Okay, so for that you have what are called graphical processing units or GPUs, which is a special chip which has thousands of parallel cores. Right? Normally for our calculations, we cannot do 1,000 things in parallel in our programs, right? It doesn't exist. So normal computers don't need CPUs. But if you have computers that are doing all of these machine learning stuff, for machine learning, a lot of the algorithms are basically just matrix multiplications, right? You have large matrices, you have to multiply them. A lot of linear algebra you did today will be useful if you do a course on AI/ML. So matrix multiplications or all matrix operations, you can parallelize them easily. You have a 1,000 by 1,000 matrix. I can parallelize it on 1,000 cores by giving like each row, column, whatever to a different core, right? So for such workloads, when you have to do such tasks on your computer, you can get a GPU which has a much higher level of parallelization, right? So NVIDIA today is a very hot company because it makes these GPUs that people are buying to do all the AI/ML kind of algorithms. Okay, so normal computers don't need them as much, but specific workloads, that graphics or machine learning workloads, have a lot more scope of parallelism and they can run on GPUs. Okay,
Are there any other questions?
yes. Yeah, so they'll deadlock, right? On the same, if it depends on the semaphore's initial value. If the semaphore's initial value is say 10, 2 threads called down, nothing has happened. 1 and 2 threads called down at the same time, then the first thread goes through, the second thread waits. So again, this down operation, I have not told you one thing. I was kind of expecting somebody would ask this question. What if the down operation also happens exactly on the same time and you have the... So what I didn't tell you is the way the down operation is implemented by the operating system, it ensures it happens in a one after the other fashion. Okay, this race condition or that irritating problem will not happen with the semaphore counter also. Okay, so the operating system takes care of that, right? So the down will happen one after the other. Okay.
Any other questions? Okay.
Oh. Yeah. Yeah, so that depends on your operating system. It will by default find any core that is free, that is not doing any other work, put it on it. Or you as a programmer, there are tools available where you can say, I want to run it only on this core. If for some reason you like you have a favorite number, you can pick that core and ask it to run on that core. So we as programmers have a little bit of control on which core to run it on. But if you don't do anything, it's the operating system that handles it, right? The main job of the operating system is to do all of these, to help you create threads, to run them in parallel, make sure you get all your parallelization gains and all of that. Okay.
Okay, if there are no more questions, let's thank the speaker once again.
Okay, thank you all.